So let's take a minute to talk about power and statistical significance. And before we talk about it, the baseline of this discussion is the idea of the null and alternative hypothesis that we talked about last semester, right? And so the basics of the null hypothesis is that there is no difference or no relationship. So typically, we're trying to find differences between populations, right? That's our t-test, our univariate analysis. We're looking at differences among various populations. And then in correlational analysis, our bivariate analysis, and regression, then it's that there's no relationship, right? The variable x does not relate to variable y. And same thing as we get into multivariate analysis, same thing, we're looking for relationships. So the null hypothesis is that there is no relationship. The alternative hypothesis is that there is a relationship, or in the case of a univariate, that there is a difference between populations. So that's the basis. And power and statistical significance are about whether or not we can draw conclusions about these hypotheses. So one of our concerns is that we make an error, and there are a couple ways to do that. So there's one of two populations. Either there are differences or there is a relationship, or there are not differences or there's no relationship. Those are the two things that could exist, right? Capital T, truth. On the other side, in terms of our decision, we either reject the null hypothesis, accepting the alternative hypothesis that there is a difference or there is a relationship, or we fail to reject the null hypothesis, in which case we say, well, we don't really have enough evidence to conclude that any differences we see or any relationship that we see are due to anything other than chance alone. Well, we might get this correct, right? So sometimes there are differences in the population and we reject the null, or there are relationships between two variables and we reject the null, accept the alternative, and say, yes, this exists. That's one example of being correct. The other example of being correct is there are not differences in the population, and then we fail to reject the null hypothesis. And we say, well, there's no difference and we didn't find one. Or there is no relationship and we didn't find evidence of a relationship. Both of these would be a correct conclusion. However, we don't always get to the correct conclusion. Sometimes we make an error. And when there's two types of error. There's the type 1 error and then there's the type 2 error. So the type 1 error occurs when there are not differences in the population, and yet we still reject the null hypothesis, accepting the alternative, and basically we declare that there is a difference or there is a relationship, even though there is none. On the other side, a type 2 error is when there are differences, but we didn't detect them. We didn't see them for whatever reason, so we conclude that we don't have enough evidence. Both of these are possible. We really try to minimize the chances of type 1 error, and that's where alpha comes to play, right? So alpha equals 0.05 means that we want to make it 5% or less chance that we come to a wrong conclusion about whether or not there are differences. We're oftentimes willing to accept a bigger chance in the form of beta that we make a type 2 error. Now let's talk about where these errors come from and how this works. So here we have the tale of different populations. So we have here we have the red population and we have the blue population. And this is on some variable, right? So this is the means of a certain score or something like that. So an example might be, let's say for instance that this is this is your ability to do something, and your ability to fill out a form, let's say. And so we measure people's ability to fill out a form. And the red population represents everyone ever who has never received training on how to fill out the form, right? So this is their distribution of their ability to fill out this form. And then the blue line represents everyone who has received training on how to fill out the form, right? And so and their average or their distribution of their ability to fill out the form is represented by the blue line. The difference here is not that significant, right? So if we look at A, we see that the difference is not that big. Training is not really doesn't really make that big of a difference. If we look at B, this is maybe a different training program that brings about a much bigger difference, right? And so this is an example of effect size. This has a relatively small effect size. This is a relatively larger effect size, right? So by doing the training here, doing training B, we really bring about a significant change, an important change, a practical change. In doing version A of the training, maybe there's less of a change. why this becomes an issue is, let's say we did the training, right? So, or let's say we have a particular person. We're trying to say, okay, did they go through the training? So we want to know if the training was effective. And so in order to find out if their training is effective, we take a sample and then we measure what the mean of the sample is. And let's say the mean of that sample is 1, that their ability is 1, right? So that would be this line here. Well, to my null hypothesis would be that there was no change. They didn't receive training and that there's no change in their ability. And my alternative hypothesis would be that no, there has been an increase, that there is a difference here. Well, if their mean is 1, I can't really reject the null, right? So that could be that they are part of this red line. They could be part of this no training group. It's only when they're out here in the reject region that I would reject that null. So in this case, I have made a type 2 error, the probability of which is beta. If, on the other hand, their average had been 2.5, then I would have rejected the null, and I would have accepted the alternative and said, yeah, they received the training, or the training was effective to move it in that direction. The other side of that is if, for instance, they had not, in fact, received the training, and I took this sample, and they were still over here, well, then I would have a type 1 error, right? Because I'd rejected, and yet they had not received the training. What I really want to illustrate here with these two diagrams is the importance of effect size. So you see, as the training is more effective, right? So in this case, the training is less effective. There's a smaller effect size. In this case, the training is more effective. There's a larger effect size. You see that the alpha region, the probability of alpha, does not change with effect size, but beta does. The chances of making a type 2 error where I don't detect the difference, that can change with effect size. And that's what's really important here, is this idea that power and the chance of making a type 2 error really depends on effect size. So let's look back at this chart. All right, and this is where we're talking about here. This idea that I rejected the null hypothesis, even though I shouldn't have, that there are differences, right? So my test may not have been powerful enough, right? So a test here may not have been powerful enough to have detected that the people went through training. Whereas if it's down here, maybe it is powerful enough, depending, right? So maybe 1 isn't a good example, but 2, right, is the example here. Where so if they got a 2 here, then I definitely would have rejected, right? Here, well, same thing. So, but the point is that effect size makes a difference here, and beta now is this chance of a type 2 error. Well, 1 minus beta is what we call power, right? And power is another word for sensitivity. How likely am I to be correct, to correctly identify that there are differences in the population, or that there is a relationship between two variables? And that's really dependent on effect size, but it's also dependent on a number of different things. It depends not only on effect size, but also where I set alpha, and also the sample size. So it's all three of those things together: effect size, alpha, and sample size. Effect size now, so here we have examples, and this is table 1-1 from the hair reading, right? And it looks at, these are different sample sizes, so 20 people, 40 people, 60 people, up to 200 participants. And then these are different alpha levels, right? Remember that alpha is set by the experimenter. It's set by the researcher. So if we set an alpha of 0.05, that gives us these two columns. If we set an alpha of 0.01, which is a more conservative test, more stringent, that gives us these two examples. And now we look at the effects of effect size. So in the first place, we look at a small effect size versus a moderate effect size, right? And again, if we look at this chart, this is a small effect size. This is a moderate or large effect size, right? Where you see there's an actual difference in the populations, or there's an actual relationship. And what we can see here is that when there is a moderate effect size, in order to get the same level of power, right, it actually takes a good deal more population, right? So let's take, for instance, so about 0.3 power, right? So this is 1 minus beta, or powers. 1 minus beta is here, in this case, is 0.3. Well, if we have a moderate effect size, we only need about, if we have a power of 0.3, to get a power of 0.3, we only need about 20 people. On the other hand, if we have a smaller effect size, we actually need a lot more people, somewhere between 100 and 150 people. Now, I will say the rule of thumb is 0.8, right? So we typically want a 0.8 power. So in order to get a 0.8 power, that's a sensitive enough, that's our rule of thumb, with a moderate effect size at an alpha of 0.05, we need at least 80 people. If it's a smaller effect size, we're going to need well over 200 people, right? So it's actually going to be a lot more. That becomes even more constrained if we make a more stringent alpha, right? So here, alpha more conservatively is set to 0.01. Here, to get to that 0.8 power with a moderate effect size, I need 100 people, right? So 20 more people than I did with the 0.05 alpha. And then again, I would need really a lot more to get to that 0.2. Here's the takeaway here. Power depends on effect size, alpha, and sample size. Let me show you this in a different way, right? So this is figure 1-1, again, from the hair reading, right? And here we say we're assuming an alpha or an effect size of 0.35, right? So somewhere between small and moderate. So fairly small, right? That's not really a thing, but somewhere between small and moderate. And again, that suggested power level of 0.8, right? So we have power here, and then the sample size needed in order to detect a difference, right? And so what we see is at the alpha equals 0.05 level, we see a steady increase in power as we get more and more people in the group, right? So here around 30 people with again, effect size of 0.35 and an alpha of 0.05. With 30 people, we have a power of about 0.24, 25, something like that. In order to get up to 0.8, we would need 130 people. In order to get with a more stringent alpha, right, we would actually need something over here. This is a alpha of 0.01. We'd need 190 people in order to detect that effect size at the suggested power rate. So again, the point here is that given the same effect size, if we're trying to go at a certain power level, we're going to need more people. What's the bottom line? One, we typically hold alpha constant. By general agreement, alpha is equal to 0.05. Now, there are times when we're more conservative, right? So we learned last semester that even when we do a one-tailed test, even when we do a two-tailed test rather than a one-tailed, right, we still, or when we do a one-tailed instead of a two-tailed, we always take the more conservative, right? So with our rejection region is still the two-tailed rejection region, even if we're just doing a one-tailed test, right? Because a one-tailed test with a larger rejection region just kind of gets us out of some stuff. So that's an example of a more conservative, where actually our tail is actually half of what we thought it would be. Or if we learned about when we talked about ANOVA, the Bonferroni correction, right, where we divide alpha by the number, this is about the family-wise error rate, if you remember that. We divide alpha by the number of tests that we do. There again, we see that would be a more conservative version. So typically as alpha is constant, but sometimes it's more conservative than 0.05. And in those cases, we have to understand that it's going to be harder to detect. We're going to have lower power with a more stringent alpha. We don't really control effect size, right? And so the effect size is what exists in the population. It's the difference between our two populations, or it's the strength of the relationship dictates the effect size. For larger effect sizes, I don't need as many people. I can detect those. I don't need as sensitive a test, which means I don't need as big of a sample size. For smaller effect sizes, well, I need a more sensitive test, which means I need more people, or I need to lower alpha, but I don't do that, right? So if I'm going to keep alpha constant, I'm going to need more people. Now, I say we don't control effect size, but sometimes we can. And the reason I put training here is, like, if I'm doing a training exercise, I need to see if training has an effect. If I make sure that my training is really, really, really good, that controls the effect size, right? Or if I just kind of do a halfway training, then maybe I'll have less of an effect size, right? So that might be a way that I control the effect size, is making sure that the effects that I'm looking for are really built into the experiment as well. Another way to do this is something we call extreme groups design. So for instance, if I want to see the effects of smoking on lung health, rather than looking at it across the entire population, I might take one group that has never smoked in their life and another group that smokes 6 packs a day, right? And so these are what we call extreme groups. And in this case, I'm likely to have a bigger effect size because there's nothing attenuating it, right? I'm not looking at the people who only smoke a couple of cigarettes a day or a couple of packs a day. I'm looking at either 0 or 6. That's an extreme group design. We'll talk about that more a little later, but those are ways that I can kind of, through the back door, affect or influence effect size without having to change the sample size I need or without having to change the alpha. That will make for a more powerful test. So in the most cases, power is really going to be dictated because alpha is more or less constant. The effect size I don't have a lot of control over. It's really going to be dictated by the population or the sample size that I use. One last caveat here. It is possible to have too much power. If I get a big enough sample size, I can detect even the smallest of effect sizes, right? So I can detect, 0.1 effect size or a 0.01 effect size. It can even be statistically significant. Let's imagine that I detect it across 1 million people, right? If I take 1 million people, I'm going to detect effect sizes that are really, really small, and I'm going to say, well, they're statistically significant. So we have this idea in statistics called practical significance, where we say, okay, your sample size tells you that because you have such a large sample size, yes, this is a statistically significant difference. But the question is, does it have practical significance? And that's where we really look to effect size, right? Effect size really is about the practical significance. We looked at various measures of effect size last semester. We looked at Cohen's d. R is a measure of effect size, a correlation coefficient. Beta, our standardized regression coefficients, are also sources of effect size, right? So they tell us a little bit about practical significance. And in the real world, that's typically what we use when we talk about practical significance. If the effect size was big enough, right, bigger than 0.2 or 0.3, then we say, okay, it actually has some practical significance. If the effect size, whether that's a correlation or a Cohen's d or a beta, a standardized regression coefficient, if it's less than 0.2, we start to question if it's practically significant. Now, technically, if we're going to talk about practical significance, we say, practically against what? And it's against the cost, right? Is the effect size, does it justify the cost of whatever we're going to do, whether that's in terms of time, in terms of money, in terms of effort? Is that justifiable? In reality, though, we rarely look at it that deeply. We just really look at effect size. And if it's a big enough effect size, we're willing to say, okay, I detected this, and it's important, even though I had a big sample size, for instance, it's still a big enough effect that it makes sense. So we need to take a look at power. We'll talk more about it throughout the semester. Towards the end of the semester, we'll talk about choosing samples, but we need to have in mind this idea that sample sizes, a bigger sample size makes a test more powerful or more sensitive. A smaller sample size makes it less powerful and less sensitive and harder to detect those smaller effect sizes.